today I'm going to talk about some of the perspectives we have at Ayar Labs and some of the work that we're doing to really try to usher in what we're viewing as a paradigm shift to optical I/O. And to start, I want to just look at one application that's driving the kind of urgency of this paradigm shift. And this isn't the only application, but it's certainly kind of one of the most egregious. And really what's happening is there's kind of a new space race happening in companies trying to build larger and more capable AI and machine learning machines. And here's just one snapshot that shows how fast this field is progressing and how insatiable their demand for compute is. So this is a slide that Google showed at this year's Hot Chips, and it just shows the last couple of years of progress. And the interesting thing is to look at the size of the neural nets that are being trained on these compute machines. And in less than 2 years, this field went from training neural nets of size of around 400 million to 1 trillion in about 18 months. So you're really seeing kind of a larger than 1,000x growth of demand for some kind of compute every 2 years. And it doesn't look like this is slowing down as we look forward in the next few years, as long as the compute can keep up. So, of course, the next question is, well, how do we fuel these compute needs? We're seeing broadly that the application demands are growing in the size of the problem to be solved. And AI and machine learning is one example, but you see this in high performance computing, graph analytics, in various kind of cloud data center and high performance workloads. And the general trends is these workloads are far too large to fit onto a single compute ASIC. Even a most advanced node, CMOS node kind of digital ASIC. And the desired solution coming out of the computer architecture world is that you continue to scale this computing power by interconnecting many compute ASICs together to build larger systems that are physically distributed but logically unified. And one way to think about that simply is we can start thinking about a compute rack as the new kind of logical compute node. And there are a lot of challenges to achieving this. So it's very interesting to go look at, well, how do we achieve this, and where does kind of technology sit today, and where do we need it to go? So one simple way to look at this is the chart that I'm showing here, where the x-axis is plotting the scale or the size of a computing system that you're building in number of nodes. And the y-axis is plotting the bandwidth per node. And if you look at where we're at today, these kind of break up into, let's say, roughly 2 clusters, where there's a cluster that are HPC-like fabrics of people building large high-performance computing machines. Usually governments are investing in these machines, and then some private industry. And you can get on the scale of 1,000, 10,000 type nodes, but your bandwidth per node is fairly low, typically well below a terabit per second. Now, there's also been the emergence of what we're calling DGX-like fabrics. And of course, NVIDIA is the one who kind of spearheaded this new architecture of building these high performance memory semantic type fabrics for AI and machine learning. And those you can get higher bandwidths per node, but you're limited to, let's say a dozen or around order of magnitude 10 nodes. And where everyone wants to go and where we want to be tomorrow is, scaling up into the hundreds of nodes, thousands of nodes, and ideally tens of thousands of nodes. And all of these nodes are accessible through either a single hop or at most 2 hops of some high performance low latency communications fabric. Now, the architects who are building these systems have recognized this in the need to go in this direction. And you can look at people building HPC machines and running HPC workloads, such as a quote here from Lawrence Livermore, one of their kind of head architects. And they're recognizing the need for optical I/O to come in and really change how we build out high performance communications fabrics. But you can also see this coming out of the leading companies who are kind of on the forefront of AI and machine learning, such as OpenAI. And they've recognized that to continue to scale their systems and their capabilities, they need a low latency, which is actually a key kind of metric here, high bandwidth optical interconnect to continue kind of scaling into the future. So now I want to kind of pivot and take a little bit of a look at why we can't get there today and where the gaps are. And to kind of simplify this this technical story, I'm going to walk through this chart. And this chart is really kind of a qualitative cartoon that that just tries to outline the issue at hand. On the x-axis is a kind of logarithmic scale of distance or reach, and on the y-axis is a kind of qualitative logarithmic scale of energy efficiency and density. And if you look at how the IO solutions break down across this x and y axis, it really falls into three regimes. You have regime one, which is, let's say chip scale and package scale IO. Regime two, which is board scale, and regime three, which is board to board or rack to rack scale. And the energy efficiency and the density really falls off rapidly across these three regimes. So if we look at regime one, where you have chip scale or package scale electrical IO, the IO figures of merit in this regime are highly efficient. The energy efficiencies are very good. You can get sub picojoule per bit signaling in the kind of package scale regime. The densities are pretty good. You're getting up to a terabit per second per millimeter of kind of package density. And the signaling speeds kind of span a fairly large spectrum of speeds, depending on what application is being addressed. But they range from kind of low gigahertz, kind of digital speeds, and usually you see parallel IO in this area, all the way up to 50 gigabaud type signaling, but done with very lightweight SerDes that don't add a lot of overhead to the signaling. And importantly, you can see a lot of or basically all of the major SoC vendors and designers today have gone to this chiplet model of continuing to scale out their high performance processing ASICs. So whether you're looking at AMD, NVIDIA, Intel, everyone has broken apart their full monolithic design, and they're aggregating multiple chiplets onto the same package substrate. So this regime is highly efficient and is very good in terms of its figures of merit. Now, if we go look at board scale, things start to already get much worse. You're looking at around a 10x increase in the amount of energy in terms of picojoules per bit that's required to ship bits around. The density dramatically lowers, roughly another 10x hit in the density, and it makes it challenging to really ship bits around even at the board scale in a highly efficient way. And of course, to leave the board, you have to electrically go through retimers if you're wanting to drive electrical signals out of the board. And this is shown in kind of a recent reference design from Open Compute, showing how you would scale out the connectivity of a bunch of accelerator modules. And if you leave the board, you have to go through retimers. So board scale communications is already becoming challenging as the electrical efficiency drops off with distance and bandwidth. And if we look at the final regime, which is the board-to-board or rack-to-rack regime, the energy efficiencies get much worse. You're looking at between 20 to 50 picojoules per bit, depending on what exact configuration you go compare to. And densities become very low, something around 0.01 terabits per second per millimeter of edge bandwidth density. Signaling pipes are in the 16 to 32 gigahertz range if you're looking at kind of compute to compute or compute to memory connections, or 28 gigahertz to 56 gigahertz range if you're looking at networking. Either 56 gig NRZ or 112 gig PAM4. Now, the good news is there's no longer a severe penalty versus distance because if you've gone to the optical domain, there's no longer a penalty versus distance. So this penalty kind of flatlines as you go to longer distances. But the bad news is we paid a very large penalty to get here. So the overall kind of figures of merit are very low in terms of the IO figures of merit. So really the question becomes, how do we build a new approach to combine the efficiency and density of in-package electrical IO, which was this kind of regime 1 figures of merit, with the reach of optics, which is out in regime 3, which flatlines the kind of the figure of merit penalty versus distance. And so put another way, we want to take today's optics, we want to shrink them by about 100x in size and aggregate a bunch of functionality, and also reduce their power by around 10x. And this is what we think we've achieved and what we're pursuing with the product that we're building at Ayar Labs, which is a microring based optical IO chiplet. So what does this new technology look like? Well, it starts with the actual optical device that we're using, which is a microring resonator. And this device is around 1000x smaller than the kind of status quo optical devices being used in transceiver products today. And it has high speed capability. We can get, we've demonstrated up to 112 gig or 100 gig PAM4 signaling, and others in the field have also demonstrated these kind of high speed signaling capabilities using microrings. And we've also shown that these are actually quite easy to build in 300 millimeter CMOS manufacturing processes. But it doesn't stop with the device. You have to build on top of that device. But because we have a small device in CMOS, we can integrate basically all of the transceiver functionality very densely onto a single chip and start to build these kind of very tightly integrated electronic photonic communication systems. And so we integrate all the TIAs, drivers, equalization and control, and the photonics, waveguides, modulators, detectors onto a single CMOS chip. We don't integrate the laser on this chip. We integrate that outside of the package. So you end up with an optical chiplet, and we call our chip the Terafy chiplet. So that's short for terabit phi. And we now have a chiplet for in-package optical IO, and it's capable of multi-terabit per second per chiplet at less than 5 picojoules per bit of energy efficiency. And because we have an optical chiplet and it's a CMOS chiplet, we can now build these multi-chip SoC packages, and we can integrate these chiplets inside the same package as SoCs. And when you do this, of course, you get direct from the package optical IO. So over the last couple of years, we've done a variety of demonstrations to show the power of this approach. One of which is that we integrated our optical IO chiplets inside the same 2.5D integrated package as an Intel kind of off-the-shelf FPGA. So this is Intel's leading FPGA, their high performance FPGA, and we co-packaged our Terafy optical IO chiplets in the same package substrate. And this already starts to show the power of the chiplet approach as well, because there are other chiplets integrated inside the same co-package. So for example, in this demonstration, we had 2 Terafy chiplets, but this middle chiplet is a high-speed electrical SerDes chiplet. So you're kind of able to mix and match high-speed optical signaling with high-speed electrical signaling, and it gives the ability to kind of craft the right balance of these things depending on the application. And this is me just holding up what that actual packaged form factor looks like once fiber is attached to it. So we think that this is a very compelling direction to be heading in, and we've shown all the prototype functionality in the overall kind of optical IO architecture that we're building to be functional and to be very viable in terms of functionality and manufacturability and overall performance. So we've done a variety of demonstrations. This is just one of them showing our remote laser source being sent into this multi-chip package FPGA demonstration board. And the FPGA is sending bits through our Terafy optical IO chiplet and shipping those bits outside of this board optically. So I want to touch a little bit on where this technology is coming from. Well, we've been working on this technology for more than a decade at this point. It started with a lot of low-level research happening in the universities, mostly at MIT and Berkeley, where we were working on the device and in process integration R&D. And that work really resulted in the first ever monolithic microring transmitter demonstrated around 2011, 2012. We then started working on integrating these into more kind of higher functionality subsystems and showing full transmitter, full receiver kind of operations. And then we kind of pulled all this together to demonstrate the first ever CPU chip with optical I/O directly on that same chip. So the CPU cores were actually communicating optically from that single chip. And this is around the same time that we launched Ayar Labs. Now, inside of Ayar Labs, we spent the first couple of years working on technology prototyping. Importantly, we also established a very close and strategic partnership with GlobalFoundries. And since then, in the past few years, we've been working very closely with GlobalFoundries to kind of build our full optical chiplet prototypes and simultaneously work on standing up a next generation 45 nanometer silicon photonics process with GlobalFoundries that we're going to scale into production. And we're now actually at the point to where we announced last week with GlobalFoundries that we have first working silicon in this next gen silicon photonics process with GlobalFoundries, and we're very excited about that progress and where it's going. So I'm going to talk a little bit more about that on the next slide. But to summarize this work, all of this work has led to a very robust patent portfolio. We're at over 60 patents in the kind of domain of optical I/O that we've filed over the course of the last decade or so. So I want to talk about the progress we've made with GlobalFoundries because it's very important to scale all this work into 300 millimeter foundries. So we now have the first functional demonstrations coming out of this new GlobalFoundries 45 nanometer process. And we're the first to be showing circuits and photonics functionality in this process. We simultaneously have stood up all of the automated 300 millimeter electro-optic wafer level testing that's needed to both scale the development of this work that we've done with GlobalFoundries, but also to develop the kind of high throughput, high speed testing methodologies to really lead into kind of industry standard CMOS style known good die testing methodologies, which has a big impact on the cost structure of how these solutions come together. And we're showing 32 gigabits per second per wavelength microring based optical signaling. And we're also showing this that we can take kind of commercial off the shelf FPGAs. And in this example, we've shown a Xilinx FPGA. It's using its high-speed electrical SerDes to talk to our Terrify transmitter chip that sends the data out optically to our Terrify receiver chip. And we're showing very clean transmit and receive optical signals as well as electrical output signals from these demonstrations.
Mark, we need to wrap up.
Okay, yeah, I'm at the wrap up. So we think that all this progress is leading to really ubiquitous optical I/O, heading into the next few years, and we're at the point to where we are trying to expand our sampling programs. So if you're interested in that, please go look at our website and fill out those forms. And just lastly, everyone says, what about the laser? And I didn't talk anything about the laser in this talk, but I'd point you to a talk that's going to be given by Chris Cole tomorrow, where we're very excited about the work that's happening in the MSA to really work on pushing forward the laser solutions for this architecture. Okay, thanks for the time.
Thank you, Mark. Thank you. So I have one question regarding the platform you're working on. So you talk about the I/O bottleneck. Also, without violating the NDA, can you let us know what kind of partners and what kind of platform you are working on?
Yeah, we've made a lot of the partnership or a lot of the work that we've done with Intel. We've kind of talked publicly quite a bit about that work, and so we're continuing to do that work with Intel. The specifics of I can't mention where that's going, but the trend is kind of very similar to what we've shown publicly, and we've expanded the kind of engagements beyond Intel. So, what we're seeing is a uniform need from all the SoC companies to escape more bandwidth from their packages. So, you can kind of look at the work that we've done with Intel and extrapolate that same approach to other SoC type of integrations in the kind of CPU, GPU. All of them are still in the high performance SoC category.
Okay, thank you, Mark.